What about you guys? How everyone go off and like travel like 8,000 miles last week? Yeah. You just stayed here? Yeah, I should have done that too. Yeah. Okay. Okay, back to our wonky schedule. So I think I spoke to some of you guys that worksheet 17 you guys did not complete on Monday. Is that right? Or you guys finished it? The one with the little hand cranked power generator. Do you guys want to go over that just to make sure everyone is on the same page on that? Or um, okay, yeah, we can talk about that a little bit. And so today we're supposed to start chapter 32, so we'll get to that. It's a pretty short chapter, just 6 sections, but they are pretty dense sections. So it would take a full, 3-4 days to cover those. Um, and then next week we're going to start chapter 31. And as Lydia, who's not here right now, noted, right, we're doing this backward, right? I'm going to cover chapter 32 first on alternating current circuits, which to me makes more sense before going into chapter 31, which is on electromagnetic fields, which we will learn that's just light. So somehow these electric fields we've been studying and then magnetic fields we've been studying, right? It just turns into light, and it's just an extremely good connection between them before we go into optics for the last couple of chapters in the book, and we'll see how far we get. Okay, we don't have to cover all of chapter 34 or all of chapter 33. I'll probably just blend the two together somehow. Okay. We do have a midterm after we finish everything on chapter 31, right? So that's just actually a week before the final. Well, 2 full weeks basically, and we'll see how that turns out. And then remember we actually have our final, the first day of final, or is the second day, right? On the 19th, as usual, being an 11 a.m. class is always like the first final round. Any questions on the schedule before we get started? Yeah, chat?
I kind of have a question about the physics lab portion. How
Uh-huh.
is that graded in
It's a completely separate class. Just pretend it's a separate class and it's completely separate graded.
so you get a separate grade for that?
Yeah, you get a different grade. So hopefully you pass both of them, right? Otherwise, you have to come back and take just the lab or just the lecture. In the future, we can talk about. I mean, we've been talking about how to combine those classes together, and that way it makes more sense for the students, right? But then what happened is that if we combine the grades, then if you do really well in lecture, but then didn't do well in lab, then that pulls your grade down, and we'll figure it out. Okay. Okay. So as usual, we're gonna have our start of chapter birthday. It happens to be this dude, Leonardo da Vinci. He's kind of a neat little person. I learned about him since I was a kid with Ninja Turtles somehow. I think, right? Yeah. He's actually not just a artist, but also a great inventor. And back in those days, you kind of both at the same time, right? Invented the glider, um, various. He had a concept of a helicopter. I don't think this ever worked, right? He made a spring motor, basically using spring to drive a car. Uh, what was the other things they did? He did some water wheel stuff. Where is this little water wheel thing? Um, he had this invention where, in order to have water go up in elevation, you just use a little corkscrew as opposed to bringing it one bucket at a time, and it was kind of a little neat invention. He also was credited with inventing the parachute, because if you're gliding, right, it's good to have a parachute on you. I'm not sure he does the gliding himself, but it probably gets his little minions to do it, right? Okay. So as I said, let's just go over the worksheet you guys did on Monday real quick, right? And this is the worksheet I just kind of copy and pasted it to the notes, right? We have a little circuit here where we have a light bulb, and remember light bulbs, you can just pretend there are resistors, right? And then we're going to have a little crank here, and somehow, right, just cranking this around in a circle somehow produce electricity to light up your light bulb somehow. And how does that happen, right? Okay. So the first step is telling you to just determine the magnetic flux. Remember, magnetic flux is actually this complicated equation here, right? Right. B dot dA, right? And it's just the amount of magnetic field that's going through some loop, right? In this case, it's actually kind of complicated because, right, as you turn this crank, right, you don't lose the entire area of this whole thing. You only lose like a circle part of it, right? You just lose the circle part of it. So in this case, right, what happened is that you have the magnitude of the magnetic field, right? And then the area, and we'll talk about if there's a factor here, right? We're going to write it as a function of f and t. And the last thing I left you guys with before I ran off and flew out to New York was that you can quantify these, circular motions as some sort of cosine or sine function. And if you quantify it as a cosine function, it's going to have this factor 2 pi f times the amount of time, right? Where this is the time dependent part, okay? And we have to be a little bit careful here, right? Where, right, if I have this circle oriented upward, right, I'm going to add half the area of a circle here, right? But if I'm going to have this part of the circuit flip downward, let's say like this in this orientation, right, I'm going to lose half the area of a circle, right? Does that make sense? Right? So in this oscillation, since this cosine is going to go from +1 to -1, +1, -1, +1, we're actually going to be gaining and losing half the area of the circle as this oscillation happens, right? So therefore, there's a factor of 2, 1/2 here, right? We're only gaining half a circle, losing half a circle, gaining half a circle, losing half a circle. Does that make sense? Okay. And that's basically the first part of the problem where you have to just write this quantity somehow, write this equation somehow. That's sort of the setup of the problem. Everyone got that part? Right? Okay. Now, the next thing is actually the new thing we're learning is this thing called Faraday's law, right? Faraday's law tells us that the EMF that's generated, right, by some circuit, by this little changing magnetic flux, is actually the change in magnetic flux is actually the absolute value of it, right? Okay. Okay. So if we take a derivative of this function, we should be able to get the EMF out of it. Okay, so the EMF is going to be whatever so B is constant, the area itself is constant, but you're cranking it, so this is the time dependent part, right? So BA over 2, and you need to take a derivative of cosine of 2 pi f times t, right? And what's the derivative of a cosine function? Negative sine. But since we're only worried about the absolute value of it, then we can just take the absolute value, right? So this is BA2. Since I took a derivative with respect to time, the stuff in front of the time pops out, okay? Then I get a 2 pi f in front, and then this turns into sine. Technically, you're right, it's negative sine, but we're going to see that we're going to take the absolute value of it anyway, okay? So therefore, right, the EMF is actually going to be BA times pi times f times sine of 2 pi f. Oop, I forgot the t, right? When you take the derivative, the time don't go away, right? Okay. But we're not after EMF, right? We want to figure out the current, right? The current going through this circuit should be what? Should be what? Should be 2. Yeah, I think you might have the quantity right, but what's the concept, right? That if we have a current, if we want to figure out what the current going through here, right? This is some resistor. If you have a resistor and some current, that gives you which law? Remember? I'm sorry? Ohm's law, yeah. So we use Ohm's law to figure out the current, right? In this case, right, the change in potential across the resistor is going to be the EMF, right? Because that's the only object in your circuit, okay? And that's going to be IR, right? So I over the EMF over R is going to give you BA pi f over R sine of 2 pi f times t. And here's maybe the connection to the concept to the next part where we're trying to figure out how fast you have to crank this thing, right? Because I think the next part it says solve for f. right? Right. This is a time-dependent function where it's some current that depends on time. We're going to see that in a second here. Right, it's a sine function, so it's going up and down, up and down, up and down like this. Right. When the current is at the maximum, right, that's when you're delivering the most power to the light bulb, right? The more current you deliver to the light bulb, the more power it will get, right? And speaking of power, right, so the power being delivered to the light bulb is just the pretending it's a modeling as a resistor is just I times V, right? In this case, V is just the EMF, okay? So we need to figure out somehow how to convert this to figuring out how fast we need to do this, right? So if we go back up to here, this little light bulb has a resistance of 1 ohm and has a power of 4 watts. The way we figure those out is by just looking at the units on the right, right? It doesn't tell you that the resistance, but you know what the units are, so you actually know what it is, okay? So the power should be 4 watts, okay? Okay. And then the resistance, right, is 1 ohm. But on the right-hand side of this equation, we don't have resistance, so somehow we have to convert that to resistance somehow, right? So since using Ohm's laws once again, right, we can plug in here. This is actually, instead of EMF, we can make that into I times R. Oops, yeah. So it's actually I squared times R here, right? That's the power we're talking about, okay? So from this, we can actually calculate what is the current that has to go through that bulb in order to figure out um, how much, whether or not it will light up, right? If we have this amount of current, then the light bulb will light up. If not, then the light bulb will not light up, right? And solving this for I, we get power of R over R, right? And then I think as Isaac already stated, right, since the power is 4 watts, the resistance 1 ohm, right? If you take the square root, these are all SI units. They should all cancel out and give you amp as the answer. So the amount of current that you need to go through the light bulb is actually 2 amps. Okay, so that's what we want this value to be. Okay, okay. Therefore, right, if you solve this equation for F, right, and the idea is that, well, what about this, sine times 2 pi f thing, right? That's just an oscillation because we're trying to figure out how, at which point, right, the light bulb would light up, and at the maximum amount of current, right, we're only interested in the maximum or minimum amount of current. It actually does both, right? That's when we will get the light bulb to light up. Basically, the light bulb will just kind of blink, 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 okay? Right? Because at this point, right, the current is actually 0, right? It actually doesn't light up, okay? And we're going to see how fast it blinks, okay? So since we're interested in the maximum current, right, so we're going to say I max is actually this factor in front without the sign of 2 pi f times t, okay? So this BA, oops, there's no 2, times I times R, right? This has to be equal to 2 amps, okay, somehow. Okay, now we can actually solve this equation for F, right? F is going to be 2 amp, right, multiplied by R divided by the magnetic field times the area of a circle, and then there's a pi on the bottom also, right? If you plug all these numbers in, what you will see is that the frequency is actually going to be 406 hertz. Okay, so this light bulb is going to be blinking 406 times per second. Okay, and that's why you actually don't see it blink, because it blinks so fast, it's faster than what your eyes can perceive. Okay, so it just kind of looks like a constant light. In fact, this is happening with the lights that's in here, and also the projector light. All these fluorescent light is actually blinking at about 120 hertz. The problem is that humans' eyes are just so slow, we don't actually see the blinking. Okay, so if you actually have like a slow motion camera in here and actually take a video in here, you're going to see the light turn on and off, on and off, on and off, on and off. Okay. Okay. Any questions about this? Okay. we're going to go to chapter 32, which is going to be the AC/DC thing. Okay. There's this little website you can look at, this little poster where back in the late 1800s, right, these two guys, Nikola Tesla and Thomas Edison, were having this little feud that, one of them was wanted to make the U.S. electricity system alternating current, right? One of them wanted to make it direct current. Do you guys remember what alternating and what direct currents are? Remember? Okay. Who do you think won? Edison won, but we're using which system? We're still using AC. So even though Nikola Tesla was right that alternating current is actually a better way to deliver energy in the large scale, Edison had more political connection, and he's not, Tesla is just kind of an odd person also, so he wasn't good at like convincing politician um, to give him credit for basically setting up the entire U.S. Power grid system. And it's just a little interesting story when you guys are going to be scientists. You're going to have to deal with people who are non-scientists, right? Who actually decide what you get to do, right? So this is something that's an interesting lesson where, but basically your social, your political, and your writing skills are also very important, not just your scientific skill. Because definitely, I think Tesla was a better scientist, but then Edison was just a better writer and be able to explain what he wants to with people. Okay. Anyway, so that's a little bit of an interesting history, but going back to physics, right? In chapter 26 and 27, we study all this stuff called direct current circuit, right? This is when I gave you guys a battery, right? And then I connect some resistor to it, and we're trying to figure out how much current, and we did this Kirchhoff loop law stuff, Kirchhoff's junction law, and Ohm's law stuff, right? All of that is going to still apply to alternating currents, okay? And in fact, I think I already talked about this. I don't like the name alternating current because even though the current is alternating, just like what we did with the little generator, the little hand crank generator up here, it's actually much easier to control the circuit by alternating the voltage instead. You can control voltages very easily, but you cannot control current very easily. Okay, and we're going to see why this happens. Okay, but AC/DC sounds like a cool name, but then alternating voltage, AV versus DV, is just a tongue twister. That's why people don't use it. Okay, so let's talk about what an AC power source is compared to what a DC power source is. Okay, we're going to see that we're actually varying the voltage, not the current. Okay, so what we're going to do is we're going to utilize the fact that, from last chapter, when we had Faraday's law of induction, we can actually produce alternating power very easily, right? Just like when we're cranking, and it's the same idea that allows power generator from either a fission power generator or a coal power generator or a windmill. They all generate alternating current because what you're actually doing, right? The way you actually generate power is by basically converting, right, mechanical energy, meaning stuff going around in a circle, into electrical energy, right, which is what your current is, right? Somehow, right, Faraday's law allows you to make this connection, right, between mechanical energy to electrical energy. Okay. So let's just assume for now that we're going to have this alternating current voltage source, alternating voltage, right? Where let's just plot it as a cosine function, but even if it's a sine function, we can just shift this around, right? Shift this x-axis to somewhere, sorry, this t-axis to somewhere where the 0 is going to be in the right place. So we just have some cosine wave, right, where you start off at the maximum amplitude, right, and it oscillates down, up and down, and the amount of time it takes for the voltage to oscillate, right, from in one period is known as the period of that oscillation. right? And we did all these little calculations from, ooh, I don't remember what chapter. Was it chapter 15 last semester? Right, if you look in the textbook, we did all of this oscillation stuff, right, where the period is 1 over the frequency, and then the frequency is like 1 over 2 pi omega, where omega, right, is the angular frequency, right? Let's just define that, right? It's known as the angular frequency, okay? Right, and then t is the period of the oscillation, and then f is the frequency of oscillation. All three of these variables describe the same thing, right? You can convert one to the other very easily, right? And we're going to see why we have three of these things instead of one, because sometimes it's just easier to understand the concept in terms of period. Sometimes it's easier to understand the concept in terms of frequency, sometimes in terms of angular frequency, okay? So what we're going to do is that, well, I mean, we're going to have to quantify this somehow, you know, using our little mathematics, right? Where, well, if this is some cosine oscillation, I can write this function where, right, this EMF will depend on time, right? And it has some amplitude, right? Because any oscillation will have some amplitude. And it's going to be multiplied by this cosine omega t, where the omega t is actually what's making it oscillate up and down. Okay? Sounds familiar? Yeah. Okay. All right. Before we get into this, the book actually introduces you to a little technology, little math, a visualization method. Let's not even call it math, okay? Where you can think about this as, instead of thinking about this as a function that's oscillating up and down with time, right? When we did our oscillation chapter, we can also think about oscillation as an object going around in a circle, right? And the oscillations is describing the up and down motion or the sideways motion, right? It's a projection of what's actually going around in a circle, okay? So what we can do is actually, well, you can visualize this oscillation as if there is just some arrow, like a clock, right, going around in a circle, okay? And when you want to figure out what the voltage is, maybe at this point, right, you just project it along the vertical direction, okay? Let's just do, okay. I think the book does it in the horizontal direction, okay? So this is the voltage direction as a function of time, okay? And you can, if you have some particular time, you can actually figure out exactly, let's say the arrow is at this point right here, right? You can project it down here and figure out what the voltage is, right? You may think, like, I mean, we have this simple function that's going around up and down, right? Why do you want to complicate this by making it go around a circle, right? We're going to see how this will be useful when we're dealing with voltages, currents, and multiple voltages that actually oscillates what's known as out of phase with each other, okay? And hopefully we'll get to that today. Right. So that's just a reminder that things going around a circle, right? When you write the equation for the x projection of it, it's the same thing as an oscillation. Okay. All right. So let's talk a little bit more about what these alternating voltage looks like, right? So let's say you have one full period of this oscillation, okay, of this voltage source, right? At t equal to 0, basically we're going to set it so that it's at its maximum value, okay? So at the amplitude, okay, whatever squiggly E naught is, right? Okay. When we get to 1/4 of the period, we actually reach exactly 0. So the voltage actually goes to 0 at that point, okay? Just like if you go a quarter way around a 0, the x projection of it is actually 0, right? Okay. When you get to half the period, that's when you get to the negative side of the voltage, okay? So the alternating current that's actually in our wall jacks here is actually alternating from positive 170 volts to negative 170 volts, okay? Up and down, up and down, up and down like that, okay? When it reaches 3/4 of the period, it reaches 0 again, right? So hopefully that makes sense. Okay, and then it comes back to the full period, and this is when it starts over again. Okay, it's just going to repeat over and over and over again as long as your windmill is spinning around. Okay, right. So let's see what happens if we plug this voltage source into a simple circuit. Okay, and we're going to start off with the simplest thing, which is the resistor. Right, this is the thing we know how to deal with from our direct current days, right? When we did direct current, resistors are things that follow Ohm's law, right? Remember, Ohm's law is that the voltage drop across a resistor is the current times the resistance, right? So we can use that. Okay. Okay. So in this circuit here, right, we have some voltage source. Okay. Right. If we have some voltage source, we can follow Kirchhoff's loop law. We're gonna, let's say, maybe start off at this point. Okay. I'm gonna go in this direction, right? I'm going to cross the voltage source, right? So I'm going to gain whatever voltage source that is, right? Which is described by this complicated, epsilon naught times cosine omega function, right? Okay. When I get to this point, right, I'm going to cross over a resistor in the direction of the current. So I'm going to drop, right, some voltage amount that's following Ohm's law, okay? Okay. So let me just write it on the side here, okay? So I'm going to gain that EMF that depends on time when I cross this. When I get to this part, I'm going to lose whatever the voltage drop across the resistor is that also depends on time, okay? And now I get to the original point, so therefore that change in voltage has to be 0, okay? This may be hard to see, especially the way I write, right? I'm going to write this as a lowercase v, okay? Okay, it looks like velocity, unfortunately, in that case, right? When I write a variable in lowercase, I mean, I'm going to signify that, oh, it's actually a time-dependent variable, okay? Capital V will be a constant, okay? EMF is kind of weird because the squiggly E doesn't actually get uppercase and lowercase very easily, okay? Well, so that's not too bad because I can apply, as I said, right? Even in alternating current, right, Ohm's law still applies, right? But we just have to figure out what the time-dependent part is, right? So the current is going to depend on time. Oops, that's supposed to be a minus sign, okay? Okay, if it depends on time, I'm going to write the lowercase version of it. Okay, will the resistance depend on time? No, right? Because that should be something that you built, right? It just is once that resistor is plugged in there, it shouldn't change, okay? So therefore, right, we have this relationship where, let's see, should I go over here? Okay, let's just keep writing like this, okay? We have this relationship where the EMF is going to give you the current as a function of time times the resistance, okay? If we plug in what the EMF function is on the left-hand side, right, is some amplitude times some cosine omega t, right? And that's going to be equal to IR as a function of t times R. If we solve this equation for IR, the current through the resistor, right, is a pretty simple algebra problem, right, where the voltage, right, the current going through the resistor is just the magnitude of the voltage source divided by resistance times some cosine function. So it's just oscillating up and down also, right? Okay. And remember that the EMF as a function of time is actually just EMF not cosine of omega t. Okay. The important thing here is that they're both cosine function and they're both cosine functions of omega t. They look exactly the same, right? It's just this factor in front that's different. Okay. The constants are different between them. Okay. So their functional behavior is the same. So what I'm gonna do is I'm gonna show you this plot. Okay. 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 I'm gonna copy down the equation here. I as a function of t is epsilon naught over r cosine of omega t. What I'm going to do is I'm going to make this epsilon naught over r equal to big I, some constant big I, okay? Big I r, okay? It's just, since it's a constant, I can just recast it and then just combine them together, right? Because there's just once I know what the amplitude of the voltage is, I know what the resistor is. Let's say it's a 10 volt amplitude, right, with a 5 ohm resistor, right? I know that capital IR is going to be 2, but it's going to oscillate up and down, right? That's just an amplitude oscillation. Okay, so therefore IR is actually, sorry, little IR is, as a function of time, is actually capital IR, which is a constant cosine of omega t. And so we stated that we're just going to assume that the voltage source is going to be some EMF naught times cosine of omega t, right? Okay. If you plot these functions, right, it's going to look a little wonky, right? Notice that I'm plotting, this plot is plotting voltage and current on the same axis, which is very confusing because they have different units, right? But what we want to just compare is, suppose we don't care actually about how big it is. We just want to figure out, oh, are these in phase with each other? When they're in phase with each other, that means whenever the voltage and the is at its maximum value, the current is also at its maximum value. Whenever the voltage is at 0, the current is also 0. Whenever it's at the minimum, they're both in sync with each other. And then when they go back, it's also in sync with each other. So the two functions are in sync with each other, right? And this is due to the fact that they both behave, oops, didn't mean to do that. Just being mean to me. Okay. The reason for that is that they both behave like cosine function, right? One of them is not a sine function, and they both have the argument inside that function is omega t, right? Okay. Okay. So I'm going to do a phasor diagram for this. It's going to look very boring. Okay. That means if you pretend that, we go back to the idea is that, well, if the voltage source is kind of going around in a circle, and when we want to actually measure it, we're doing an X projection of it, right? So it's going around in a circle like this, okay? The current is going to go around the circle at the same rate. These two things are going to point in the same direction all the time. It's as if you have two minutes clock on your clock. They're just going to go tick, 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 tick together synchronously. Okay? This looks really boring. Right? It's like, why is he talking about this? This is really dumb. Okay? So as I said, what's the big whoop, right? Okay? What's more interesting is that instead of plugging in a resistor into the circuit, what if we plug in a capacitor? Okay? So just the main thing to take away from this is that you're going to have, if you have some voltage source that behaves as some cosine function, right? The current through that resistor is going to behave as if it's the same cosine function with the same argument, okay? And those two are in sync with each other, okay? What we're going to do is I'm going to jump to a capacitor, and this is where things get a little bit more interesting, okay? Remember what a capacitor is? A capacitor is two parallel plates. As the charges collect on one side of the plate, the negative charges actually gets drawn from the wire onto that plate, okay? And we're going to see that on a direct current circuit, the charge cannot cross this little gap, right? But in an alternating current, it actually can. Sorry, an alternating circuit, it actually can, okay? So let's see what happens, okay? I put a little capacitor, oops. Right, put a little capacitor in here. What we're going to do is we're going to use Kirchhoff's law again, okay, and let's see what happens, okay? Why did I write those notes like this? So this makes a lot more sense when I was in an airplane. Okay, let's just do Kirchhoff's law as if I know what I'm doing, right? Okay, let's start off at this point again, right, where we're going to gain some EMF that depends on time, right? And then when we cross this capacitor, we're going to lose some amount of voltage across that capacitor, right? That also depends on time. And then now we're back at 0, so it looks very similar to the resistor version, okay? Okay. did I do it this way? Or why did the book do it this way? I'm going to make the current out of phase. Okay. Okay, that makes sense. Okay. So the EMF, so solving this equation, so hopefully this is not going to be too hard, right? Right, that the EMF is going to equal to the voltage across this capacitor, right? So that's not too bad, okay? But remember that the EMF that we defined way in the beginning, right? We found that the EMF as a function of time is some amplitude times cosine of omega t. Therefore, since they're going to be equal to each other, the voltage across that capacitor, I'm going to try to write a lowercase v, right, is also E naught times cosine of omega t. And once again, I'm going to play more tricks on you, where instead of calling that amplitude E naught, right, I'm going to call that VC with a capital, where that's the amplitude of the voltage across that capacitor, okay? And that's what this equation comes from, okay? Okay. But to get to current is a little bit different than the resistor, right? Because for capacitors, we don't have Ohm's law, right? We actually have QVC, right? The charge on the capacitor is the voltage on that capacitor times the capacitance of that capacitor, right? Okay. But we're not interested in charge, we're interested in current, right? Current, if you have a charge that depends on time, current is actually the time derivative of charge, right? How much charge per time, that's actually what gives you current, okay? So since QVC still holds here, right? So what I'm doing is I'm just making this a lowercase and this a lowercase, and then C is a constant, right? Because it's just the size of the capacitor, right? So I lowercase both of these guys, right? And I plug in what the voltage as a function of time is here, right? So this is the charge as a function of time, okay? Unfortunately, the book hates writing this little parentheses with time, so I have to add this in all the time, okay? So put that in there when you're writing your notes, okay? Whenever you see this lowercase stuff, if you're not used to this yet, right, just put a little parentheses, that's it, that depends on time, okay? Right? If I take a derivative of this, I will get current, right? Because the idea is that the time derivative of charge should give me current, okay? So the current is the time derivative of charge. So if I take a derivative of this is a constant. Remember, the capital VC is a constant, right? All I'm doing is I'm taking a derivative of a cosine function. When I take a derivative of a cosine function, I get negative of the sine function, right? Okay. One more thing, right? Since I'm taking derivative with respect to time, one factor of omega pops out, right? So that's where this comes from, right? Okay. Now, right, we have a sine function and a cosine function. I'm going to rewrite these functions again, right? Remember that the voltage across that capacitor as a function of time is the same thing as the EMF as a function of time, which is VC cosine of omega t, right? But the current across that capacitor, right, is this complicated function, negative omega c VC sine of omega t, right? Now we see the difference, right? Now one is a cosine function, the other one is a sine function, right? And that's going to look different on a plot, right? Right, where a cosine function starts at its maximum amplitude, right? It starts at 1, right? But a sine function starts at 0, right? Sine of 0 is 0, okay? So the voltage still looks the same as if the resistor version of it, right? It just looks like, oh, it starts, it goes negative, it goes positive, it goes negative, right? That's what it does, okay? The current version, right, is actually, there's a negative sign in front also. So it's actually an upside down sine function, okay? This upside down sine function goes down and goes up. And, you know, once again, we're plotting these things, you know, on the same scale just so we can match whether or not they are in phase with each other, okay? So these are definitely not in phase with each other, right? Because when the voltage is at a maximum, the current is actually at 0, right? When the voltage is at 0, the current is actually at negative its maximum, right? Negative peak value, okay? When the voltage is at when the voltage is at 0 once again, over here, the current is actually at its maximum value, okay? And this is hard to picture, right? Because like, oh, it's like all this stuff going on here. This is where this phasor diagram that I introduced you to that was really boring in the beginning, right, for the resistor, comes in useful, okay? What we can do is actually, we can pretend, well, let's say we're just going to put the voltage as a function of time as if it's going around in a circle like this, okay? Just imagine a clock, right, that's going backward somehow, okay? Right? The current is actually going to be out of phase relative to the capacitors. The current across that capacitor is going to be out of phase with the voltage across that capacitor by basically 90 degrees. How do I see this, 90 degrees? Right? If you actually shift this over, let's see, I shift this over left by 90 degrees, okay? Let's do this in red. If I just took this number and shifted it over, right, I'm gonna tell you that the shift is actually 90 degrees, the two will actually match on top of each other, right? If all the numbers, if I took this green number, I moved it by pi over 2, I took this green number, I moved it over by pi over 2, you actually get exactly the same function once again, okay? I'm going to see this as coming from a trig identity, okay? So but before we get to the mathy part, right, you can imagine that these are two different hands of a clock that are going like this, right? They're moving at the same speed because they both have the same omega, right? But they're out of sync with each other, right? One of them is always ahead of the other, okay? In fact, right, you can just do a little bit of, go back to your trigonometry day, and you can actually have this identity where cosine of a negative sine function is exactly the same as a cosine function with the phase of pi over 2, meaning it's been shifted by 90 degrees, okay? So therefore, what we can do is go back up here, right? Instead of writing a negative sine function, right, we can write that as the current as, instead of the negative sign, which is what used to be here, right, we can write that as cosine of the same function, but now with a shift of 90 degrees in it, okay? Okay. Remember, pi over 2 is 90 degrees in radians, so that's why I'm switching back and forth between the two, okay? So let's summarize the results so far, okay? If we have a resistor in an AC circuit, right, the current is basically whatever the maximum current is times cosine of omega, right? And the idea is that whatever this peak current is, right, is going to occur at the same time as the peak voltage, okay? So I'm going to write is that the voltage across the resistor is in phase with the current across the resistor, which depends on time also, okay? Okay? You don't like the word in phase, just say that they're in sync with each other, okay? The two hands of the clocks are moving at the same time, okay? Okay? Where capacitors are different, right? When you write this mathematical function, you're going to end up with a pi over 2 or 90 degrees out of phase between the two, so therefore the clock are always out of sync with each other, okay? Okay? Got 5 more minutes. So I'm going to introduce this one last concept here where this is where I think I got confused by this when I took this class also. What we're going to do is that, well, a lot of times, since we have an oscillating voltage up and down, and there may be a current that's going up and down, either in sync or out of sync with it sometimes, a lot of times what we actually care about is actually just the peak value of it, right? How big is it, right? Okay. What is the amplitude of the oscillation? Okay. Okay. If we're looking at the capacitor version, okay, let's go back, this equation up here, right? The amplitude is the thing that's just in front of the cosine function, right? Right? Because if we write, so if you have some wave, right? Let's say y is a function of time, okay? This is going to be, some amplitude, some cosine omega t, right? This is the amplitude. Whatever is in front of the cosine function or the sine function, that's the amplitude, right? Okay. What we're going to do is we're going to define that as the peak value. So this IC, okay, is going to be defined as the peak current. Okay, that's what the confusing part is. Okay, we're going to try to not deal with the time dependent part as much as possible. Okay, well, one thing about the resistor, that's the reason I did it, right? Resistors in AC circuit still obey Ohm's law, right? Look at what's up here, right? This I over R here is actually exactly equal to whatever the maximum current is divided by the resistance, right? And then if you solve this equation, you end up with Ohm's law, just as in DC circuit, okay? Wouldn't it be nice if the capacitor also does this, right? Where we can solve this and have like a capacitor version of Ohm's law, okay? So what we see here, we have a current, we have a voltage, right? This thing between here, right? Let me just highlight that, right? This thing between here is like the reciprocal of the resistance, right? What we can do is then we can solve this equation for voltage, right? Just by dividing both sides by omega c, right? Now we have current times something, okay, right? In Ohm's law, right, that is resistance, right? For capacitor, right, it's not resistance, it's this 1 over omega c thing, right? It's like, what is that? What we're going to do is we're going to call that xc, okay? This is defined as the capacitor's capacitive, I think, reactance, okay? Reactance. If I can spell reactance, that would be nicer, right? Reactance, okay? It's like resistance, but for capacitors, okay? It's weird, right? Because we're talking about, actually, we'll also only talk about the amplitude of it, right? How big is that voltage? How big is that current, okay? And this is the capacitive reactance, okay? And it's defined for, in this case, since we want to just make this into XC, right? The capacitive reactance is actually 1 over omega c, okay? Be a little careful while I have a couple of minutes, right? This only applies to the peak values of the voltage, the current on the capacitor, resistors, whatever you're talking about, okay? It does not mean, right, the voltage is equal to the current times the reactance, okay? Okay, because there's going to be this cosine of omega t plus pi over 2 factor, okay? The time dependence are still a time dependence thing, okay? You cannot match them exactly, okay? But what we're going to do is we're going to play around with this idea of basically modeling the resistance, how resistive that little capacitor is to current that's trying to go through it if you have an alternating current source, okay? And what's really neat is that it actually recovers what we know from DC circuit, okay? How much current goes through a capacitor in a DC circuit? Do you guys remember? If you have two parallel plates like this, and I put a battery in front of it, how much current can go through it if I just have some voltage source there? Right? Because the bunch of pluses is going to build up there. Are any of them going to be able to cross the capacitor? Yeah, right? Exactly. The current in a DC, right, is equal to 0, right, for DC circuit, right? So let's see if this happens, okay? Right? So if you plot, right, this simple function as a function of omega, meaning the frequency, right, for DC circuit, what should be the frequency of the oscillation? How fast? If I'm standing still, how frequent am I getting to the bus stop? 0, right? Okay, so great, right? So omega equal to 0 means DC. This is basically what a DC circuit will look like. This is, high. This is known as high frequency. Okay, as we go to the right. As the as the uh, as the frequency goes to 0, basically your capacitive reactance goes to infinity, right? It's as if this has like infinite resistance, so it blocks any current from passing through it. Okay, so that makes sense, right? It's just like the same as what we learned, right? But as you increase the frequency, it becomes less and less resistive to current passing through it. Okay, and that's what we're going to play around with tomorrow, where we're going to build some study these things called low pass and high pass filters right after our worksheet tomorrow. Okay, so we're going to study how